Okay, in this video, we're going to cover adjustment of stresses. Our learning outcomes. So at the end of this chapter, you should be able to use appropriate tables for reference design values and compute the appropriate adjustment factors. The outline for the whole chapter is first, we're going to cover some of the design applications of allowable stress design method, which we talked about earlier in the previous lessons. And then we'll go to the reference design values. But first, we're going to discuss some essential concepts for us to be able to use the tables properly. And then for the third part, which is the bulk of our discussion, would be about adjustment factors, such as those listed in the outline from letters A to J. Okay, so first, allowable stress design method. As we've mentioned in the previous lessons, this is the design philosophy that will be used for 133, and it is widely used in wood design. So it's also called working stress design method. And the philosophy is that the working stress or the service stress due to the design loads will be compared to the allowable design values. The stress should be less than the allowable design values. So we have here F prime, the allowable design values, reference design values F, and then adjustment factor C. The F prime are based on reference design values and adjustment factors, which would be the allowable design value, this one here. So this part of the equation is covered by F prime. And then, for the reference design values, as I've mentioned in the outline, it will be obtained from tables. And then, the adjustment factor C. So each has symbol C with subscript of what it represents, as we've seen here, adjustment factors from letter A to J. Okay, so F prime would be equal to F times C. And then the assumption is that the factor of safety has already been accounted in every reference design value. So then this F prime would be the one, this F prime here would be the one to be compared from the working stress or service stress due to design loads. Okay, some types of design values. So we have here FB, bending stress, tensile stress, shear parallel to grain, compression parallel to grain, and then compression perpendicular to grain, modulus of elasticity. FB is, I think by this point you already know this, as well as the tensile stress. While FV, shear parallel to grain, so we have here a wood member, and as we can see here, the grain is oriented along the length of the member. And so, if it is shear parallel to grain, the direction of the shear is like this, along the length of the member. And as you can remember from chapter 2, we are dealing with horizontal shear stress. So, the small letter FV will be compared to the design value, large F, or big letter F, V, but of course multiplied later on with the adjustment factors. FC here, the compression parallel to grain, so it deals with the column behavior. So we can see if this is the grain and then our compression is oriented in the same way, so somewhere here, then it is expected to exhibit a column-like force or column behavior. While FC perpendicular, on the other hand, if this is the grain, then we have a compression perpendicular to it in this direction. Therefore, FC perpendicular deals with bearing forces. Okay, so for our adjustment factors, as we've mentioned, we have many: load duration, moisture content, and so on, as you can see here. And then from this table, we can see the applicable adjustment factors. Say for our bearing stress FB, we only need to compute for CD, CM, CF, CFU, CT, CL, CR, and then CI. And like for FC, So we only need to compute for CV, CM, CF, CT, CP, and then CI, and so on. Later on, we'll discuss this, or in the next video, we're going to discuss this stresses one by one. Sorry, the adjustment factors one by one. Okay, so before we dive in the reference design values, so we need to differentiate sawn lumber with glued laminated lumber. So sawn lumber is directly derived from the tree and then sawn to shape, while as you can see here, glued laminated lumber is derived from the laminated lumber plates. And then for sawn lumber, so we have a definition of the dimensions: width B or thickness B, and then the depth D. So sawn lumber is further classified into dimension lumber and timber, in which the thickness B is 2 to 4 inches for dimension lumber, and then for timber, the thickness is greater than or equal to 5 inches. Okay, and then we will go to the reference design values in table 4A included in your course pack. And as you can see here, so we have a visually graded dimension lumber. If your member is 2 to 4 inches thick, then you're going and it is a sawn lumber and then dimension lumber, then you have to use this table here. On the other hand, if it has a thickness of more than 5 inches, then you have to use table 4D. Further classifications of timber. So we have beams and stringers, and then posts and timbers. So for beams and stringers, these are the sections most likely used for such as beams and stringers, while this on the other hand is used for columns or posts. And then the description is that the breadth or the thickness is greater than or equal to 5 inches for beams and stringers, and the depth is greater than 2 inches plus the thickness. And on the other hand, the depth for posts and timbers is less than or equal to B plus 2 inches. In short, the beams and stringers are rectangular in section, while the posts and timbers tend to be approximately square. Okay? Concepts we need to discuss so that we would be able to use the tables properly. So we have here sizes of sawn lumber, different configurations. So it depends if it is a standard dressed size or dressed lumber, and then rough sawn, and then full sawn lumber. For dressed lumber, the lumber is surfaced to the standard net size, which is less than the nominal size. Rough sawn are timbers that are sawn to dimensions that are close to the standard net size, while full sawn lumber is the actual size. For 133, we're going to use the standard dressed size unless otherwise specified. Next, lumber grading. If you have noticed in our tables a while ago, so we have here the species of our member or our timber, let's say Alaska cedar or bald cypress, and then we have commercial grade here. So for the grade, there are two types: visually graded structural lumber, which are graded by visual inspection, while the other is machine stress rated lumber. So small percentage of lumber rated by subjecting a piece of wood to non-destructive test. Now, as the stress grade quality goes higher, then the higher the strength, consequently the higher the cost. So typical lumber grades select structural and then number 1 and then number 2. So at least for these types, the highest one is the select structural lumber grade. And then the lowest for these list at least is number 2. Okay, density of wood. So we know that the higher the density, the higher the strength generally. for wood, and it ranges from 550 to 1,800 kilograms per cubic meter. And then the average density will be used in approximating the dead weight of every wood member. In the next video, we're going to cover the adjustment factors.